So, a very good afternoon to you all. So, on the onset, I wish you all on the first National Space Day of India. So, I welcome you to the session. So, today we will discuss about Python for deep learning models. We will see how do we create deep learning models using Python. Before going to that, I will just because I will just introduce you, or actually, I think my some of the contents which I am going to tell now, maybe it might be overlapping with some of the previous speakers. So, but just for the sake of completion, I will just touch upon the basics of deep learning. And the lecture is divided basically into two parts. So, in the first half, I will be talking about the basics of this deep learning and AI, machine learning, and deep learning. And in the second part, we will see how do we make these models in action, right? So how do we make these actions using Python programming language? So here I am assuming that you have some basic knowledge of Python programming. So actually without that it will be quite difficult to follow it up. So my basic assumption here is that you all know the basics of Python programming language, right? So this is what I will be covering over the course. So over the lecture actually, so I will just briefly touch upon the AI, ML, and DL that might overlap with some previous lectures. Then I will discuss about some basic Python libraries or frameworks which people generally use for making these deep learning models. Then specifically we will use one of the frameworks called PyTorch. So I'll be just briefly introduce you to PyTorch, and in the second half we will see how do we create these deep learning models in really how does that neural networks look like in PyTorch. And because this course was all about geospatial data, so briefly I will just touch upon geospatial data, and we will see how do we use this deep learning for geospatial data. So before going to the details, so there is so much hype around artificial intelligence. So we'll start with what is called intelligence, right? So intelligence generally, if we loosely intelligence can loosely be defined as the capability to obtain knowledge and skills and to apply those skills to various situations without any specific supervision, right? That's what we call intelligence. So like we need not to be programmed specifically from some specific task. So intelligence means when we learn, or our capability to learn and acquire knowledge and skills from our surroundings and apply those automatically without any supervision to any specific or new problem which we encounter in our life. So that's what we call intelligence. Because before advent of machine learning, these capabilities were not with the machine. So right, so that was specific to humans. So intelligence is generally connected to some kind of abstract thinking or self awareness, but generally we cannot define intelligence formally. So if we say intelligence is made up of reasoning, like if you have the capability of reasoning, learning, or some problem solving skills, making perceptions about something, and linguistic intelligence, if a person or machine is generally contains these attributes, then we say that the person or machine is intelligent. So that human beings have been innate intelligence defined as the intelligence that governs every activity in our body. So our as a human we have natural intelligence. Right. So now the term comes, what is artificial intelligence? This is intelligence. Then John McCarthy has given a definition like it's the science and engineering of making intelligent machines, especially intelligent computer programs, is all called artificial intelligence. Like making a machine which has the cognitive which has the cognitive ability of a human being is what we call artificial or intelligent machine, right? So the fundamental premise of AI is to create machines that can intelligently think in the same or similar way the humans think. So that what we call, if a machine can mimic that behavior, that we call that the machine is an intelligent machine. And artificial intelligence is all about making a machine which can mimic the human behavior, right? So it is designed to acquire knowledge or awareness from its environment, its circumstances, and entities just by learning. So if we can make like then AI is concerned about making a machine which can acquire knowledge from its environment, circumstances, and maybe by interacting with humans around this. right? So artificial intelligence is an scientific discipline that studies how can we make computers exhibit the intelligence. So now the question becomes, how do we say that the machine is intelligent? So there was Alan Turing devised a test called a Turing test, so that is taken as a benchmark for deciding whether a machine is intelligent or not. So in this case, what happens, there will be a person who doesn't, he will be interacting with someone at the background, so but he doesn't know whether he is interacting with a machine or a human being. So if the person is not able to distinguish whether he is interacting with interrogating a machine or a human, so like if the person cannot infer that he is interacting with a machine, so if the machine of that level, what we call that we can say that the machine, we say that the machine has passed the Turing test of intelligence. So if a human is not able to distinguish whether while talking to that machine, whether he is talking to a machine or a human being, so in that case we say that the machine is intelligent machine. So now there are three terms called artificial intelligence, machine learning and deep learning, right? So artificial intelligence is a broader umbrella, right? So artificial intelligence is all about making a computer program or a machine which has the cognitive level of a human being, right? So that's what we call call artificial intelligence, right? Writing such programs or making such machines which have the cognitive ability as of a human, so that this entire thing we call artificial intelligence. Now there can be multiple ways of making such intelligent program or intelligent machine, right? So artificial intelligence is the entire spectrum, and there can be multiple ways for making such an intelligent program, such an intelligent program or a machine. Like you can write a very complex program with different set of rules that can mimic a human behavior, so that will called by artificial intelligence. But there is a subset of artificial intelligence which is one of the most successful technique in creating artificial intelligence, is what we call machine learning. So in machine learning, instead we don't write a very intelligent program, so we write program which learns from some previous data. So what you can say that a branch of artificial intelligence which is concerned or which makes machine intelligent by learning from some past data. So it learns from the past data, it acquires some knowledge from that past data and applies that for the specific problem which it is handling. So this what is, so machine learning is a subset of artificial intelligence which acquires or gains intelligence by learning from the past data. So this is one of the most successful technique. Then there is a subset of machine learning called deep learning, right? So deep learning is also artificial intelligence technique which learns from the past data but is learning in different. So a machine learning may be some statistical or some other kind of technique, but deep learning is a subset of machine learning which is also learning from the past data, but it uses something called deep neural networks for learning. So artificial intelligence is a broader term, and inside there is a subset of artificial intelligence what we call machine learning, which is learning from the previous data. So the learning may be in the form of some statistical similarities or some kind of based on some statistics, and a subset of machine learning where we use artificial neural networks is called deep learning. So if you see the entire spectrum of AI, ML and DL in a single frame, so artificial intelligence involves, like we can say, ability to sense, reason, engage and learn. So it involves computer vision, like natural language processing, voice recognition, robotics and motion and so on, right? And machine learning basically unsupervised learning. So because machine learning is a specific subset of artificial intelligence where we make a machine intelligent by learning from the past data. So machine learning is basically, like you can say, supervised learning, unsupervised learning, then reinforcement learning or something like that, right? So then deep learning is ability to learn by connecting multiple layers together. This is another subset of machine learning where we are learning from the past data, but our learning is not based on some statistical learning, so it is based on some neural networks. So what all we can do with machine learning algorithms? So machine learning algorithm can be used for predicting a target category. So we can use machine learning for binary classification or multi-class classification. We can use machine learning for finding unusual data points, like if you have a lot of data points, like we have the all credit card transactions taking place every day. So from that we with the help of machine learning we can identify the most probable fake transactions. So, right, so we can use machine learning for finding anomaly. You can for anomaly detection. We can use machine learning for predicting some, like instead of classification, we can even similarly we can use machine learning or deep learning for predicting continuous values in the form of regression. Then we can use machine learning for seeing how values change over the time, right? Like we can see the pattern, or we can infer pattern from the time series data and use it for inferring future values, right? So these are the some things where machine learning can be used, or all of the machine learning algorithms fit into, like maybe either they will be using they will be doing classification or regression. So basically these two tasks what generally machine learning algorithms do is classification or regression. So these are some applications where deep learning can be used in geospatial domain, like this can be used for automatic building damage assessment from the satellite imagery, or these can be used for land cover mapping. If you do these things manually, it's quite difficult, and if you are like for a single image or small area, it can be done manually, but if you want to do it as at scale, which is humanly not possible, so deep learning comes to our rescue for handling such cases. It can be used for glacier mapping and glacier lake monitoring, renewable energy mapping and all, right? So whatever we can do manually with manual stuff, so all the things can be done automatically using deep learning. So these are some machine learning techniques. I think in the previous lectures must have been discussed in detail. So machine learning techniques we can just generally classify into, say, supervised, unsupervised, and reinforcement learning. So what happens in case of supervised learning? Like suppose here there are two images, like the images of cats and dogs. In the case of supervised learning, like we have some many images of cats and dogs, and with every image we have a label also attached to that. So we train our model showing them different images and with an associated label as well. Like you can say that to the machine that this is the image of dog and this is the image of cat. So we show such many such images to the machine, and after that machine learns like this image has these kinds of feature. So this may be a dog, and if it has like whiskers and sharp ears, so then we can say that it may be a cat, right? So this way machine learns how to associate these features with the label. So this is what we call supervised learning. And in case of unsupervised learning, we don't give the label to the data. We just give the data. We don't give the label attached to that data. Like we will be showing a lot of images of cats and dogs, but we will not tell the computer that this is the image of dog or this is the image of cat. So what computer does, or unsupervised learning does, so it tries to group together, like it will just try to group them based on some similarity. Like it may try to group the images, all the images of dogs, images looking like dog in a group, and all the images looking like cat in another group. Then with the help of a manual expert, we say that these are the dogs and these are the cats, right? So unsupervised learning is all about grouping together different objects based on some kind of similarity. So another kind of learning is called reinforcement learning. So in case of reinforcement learning, like if you say the same example, so we show different images to the computer, like maybe different images of dogs and cats. So if computer says, like, or the model says correctly, like if you show it an image of dog and it replies that dog only, then we reward it. And if we say the image of dog and it says cat, then we just punish it. So this way we keep on training the images. So with this, the model learns that whenever he is saying like images has these features and if he is saying dog, then it is getting rewarded, and if it is saying wrongly, then it is getting punished. So this way computer learns. This what we call semi-supervised learning or reinforcement learning. Like if for positive thing, if the model identifies something positively, we reward it, otherwise we punish it. This is called reinforcement learning. So this was all about this. Now we will see, as we said, that deep learning is a subset of machine learning which uses artificial neural network or deep neural network for learning. So now we'll discuss about basic about. So this is a typical model of a neuron. As we say that our brain consists of neural cells. Like this is a theory of how our brain works. So our brain consists of a consists of neural cells. So every neural cell. So then in our brain we have such billions of such neurons connected, interconnected together. So they collectively work and make our cognition. So each and at the building block of our mind is what we call a neuron or neural cell. So every neural cell is having multiple inputs and one output, right? So axon and dendrites. So it has inputs that we call what we call axons and output, and there it can have multiple inputs and output will be a single output. So that what we call dendrite. So axons and dendrites can conduct electrical signals, like they receive input signals from the different sources or maybe from the previous neurons, and they do some processing and finally they conduct some electrical signals. So connection between axons and dendrites can exhibit different degrees of conductivity depending on what input signals are received at the axons. Based on that, the conductivity of that neuron cell will be decided. So so now suppose if you wish to represent the model of neuron what has been given mathematically, so you can say that neuron is a single cell which receives input signals from different sources, and with every signal there is a weight associated with every signal, and the neuron does the summation of all these input multiplied by their weight. Like we can say that xi multiplied by wi, then this so if the summation of all these inputs multiplied by their weights is above certain threshold, so that threshold we can decide. So depend if it is above certain threshold, then we say that this particular neuron has fired, or otherwise we say that this particular neuron has not fired for these particular set of inputs. Right. So this is a mathematical model of a neuron. A neuron, this is a simple mathematical model. Here we have the neuron receives multiple inputs. So these inputs may come from previous neuron or somewhere else. So and then with every input there will be a weight associated with that. So the neuron will do the like every input it will multiply by the weight of that input and do the summation of those inputs together, and that so if the summation of that input is above certain threshold, then we say that the neuron has fired, otherwise say that the neuron has not fired. So this is the one of the earliest neural networks. So one of the first attempt to implement something similar to a modern neural network was done by Frank Rosenblatt from the Cornell Aeronautical Laboratory in 1957. So it was a hardware implementation. He called it Mark 1. So it was basically designed to recognize some primitive geometric shapes such as triangles, squares and rectangles, right? So to input to that particular neuron was an image represented by 20 by 20 photocell arrays. So input to that neuron, so it was 400 inputs were there to that neuron. So a simple network contained one neuron, so or that they were calling thresholding logic unit. So the network weights, so like these weights needs to be adjusted so that it can identify the figure correctly. So these were done manually. So here you can see that this was one of the like this was the first what you say artificial neural network implemented in hardware. So this is what we discussed about previously. This is the mathematical model of a neuron. So this is a so these are all inputs and every input has an weight associated with that. So a neuron does a summation of all these inputs, then it may apply a non-linearity to that to that output, and then it generates an output. So right, if the output is above, like in the cases of neuron, it was like if output is above certain threshold, there was no activation function applied to that, then we say that the output of the neuron was 1 or 0. It was a binary actually, but in case of perceptron we apply an activation function to the summation, and output of that activation function is used further, right? So this is the forward model of propagation. So the previous picture which I showed was not completely correct. So in that, if we add an bias to output so that the output can be shifted to plus minus. So when we add so now the model of neuron, this is what we call a perceptron. So the model of perceptron is like this. It has multiple inputs and weights associated to that. So it will do a summation of all weights multiplied by the inputs. Then it adds a bias to that. So what W0 here is called a bias. Actually, these all slides I have taken from this source. W0, then it applies an activation function to that summation plus bias, so that is produced as an output of the neuron. Right. So once so then now let us see what is the use of this activation functions. So if there is no activation function in the neural network, so the neural network is just a linear. It cannot learn non-linear features, like the entire, like suppose if you make, instead of one neuron, if you make a network of maybe 10 or 100 neurons, so these entire 100 layers can just be replaced with a single neuron. So because single weight, right, because it is not learning any non-linearity, so all are linear functions. So for bringing non-linearity to our model, we attach this activation function. So there are many activation functions which bring in non-linearity. So one of the most used activation function is what we call sigmoid function. So a sigmoid function squashes the output of a neuron in the range 0 to 1. So it is like similar to what we could say probability. So probability of something also is ranges from the 0 to 1, right? So the neuron, so the sigmoid activation function squashes the output of a neuron in the range 0 to 1. So this is like importance of activation function. If our neural network, if doesn't contain any activation function, so it is just a linear function. So it can, like here if you can see these are some data points like red and green data points. So we cannot draw a linear line which can segregate these two data points from each other, right? So this is a decision boundary. So there can, so if in real world we find the data set like this. So these are two attributes of a data set, maybe x1 and x2. So we cannot draw a single line which can distinguish between these red and blue points. So we need a line like this, a non-linear line like this. So for doing classifications like this, or for bringing non-linearity to our model, we need activation functions. Right, so this is an example of a neuron. Like here you can see that this is what we can say, this is a learned neuron. So it has attached some weights, like it has given weight 3 to input x1 and weight -2 to input x2. So like this so like let's see that what does this particular neuron do, right? So this is a learned neuron. We can say that this, like artificial intelligence is all about learning these weights and biases, so that our neuron can artificial intelligence or learning is all about learning these weights and biases appropriately, so that the neuron produces correct output for the given inputs. And this is, so here we are assuming that this neuron has already been trained and it has decided that to input x1 it must give weight 3, and to the input x2 it should give weight -2. Now we'll try to see how does this what does this particular neuron is going to do, right? So here we have W0 or bias is 1 and our weights are 3 and -2. This is a vector. So input has weight 3 and output or second input has x2 has weight -2, right? Now if we apply this W0 plus x transpose Wx, so this is, if we have this is vector multiplication. So if we write like this x1 and x2, because we are doing x1 multiplied by 3 and x2 we are multiplying by 2. So now if I write like this, so this is the neuron is doing like y cap is equal to, we are applying activation function 1 plus 3x1 minus 3x2, right? So this can be just represented as a line in our two-dimensional matrix, right? So this neuron is what it is doing. So this is a decision boundary. So so if you write 1, So whatever equation we got here, from here 1 plus 3x1 minus 3x2, if you draw this as a line on our two-dimensional plane, and 0, so 0, if we equate it equal to 0, that will be our decision boundary. So what this neuron is doing here, this has a decision boundary, so it is segregating our entire two-dimensional space into two sections, maybe this and this, right? So this is distinguishing the point between these two and this. So this I learned that. Now suppose if we give a new samples comes to it with the input features with value -1 and -2. So if we, by this we can decide that to which class this particular new input fits to that, right? So this simple neuron is a classifier which is classifying. This is a classifier based on these that is given these weights to these inputs, and it specifies whether this particular input falls into this class or this class, right? So this is segregating into two different classes. So one of the problem with this single neuron was that these single neurons are good work. Like there was a paper came which proved that the single perceptron cannot learn or classify inseparable data sets, linearly inseparable data sets, right? So a single neuron is good for, like, it can segregate. If the data sets are linearly separable, then single neuron can solve the problem. But real world data sets will not be, all data sets will not be linearly inseparable. So there was a paper which proved that these linear single neuron cannot learn or cannot learn to classify linearly inseparable data sets. So this, I think this led to the winters in AI term we call. So we need a network of perceptron or a neural network of perceptron which are connected together if you want to learn or learn to classify, how to classify linearly inseparable data sets. So arbitrary depth or width may be needed, like, but neurons with an arbitrary depth can segregate all linearly inseparable data sets as well. So so if you say multi-layer perceptron or neural network has an input layer and one or more hidden layers and an output layer. So these neural networks can approximate any non-linear function. So they can approximate any non-linear function. So right, so for approximating any non-linear function, we need a network of neurons, right? So if a neural network can be as simple as with a neural network with a single layer, or if there are more than or multiple layers of neurons in a neural network, so then we call those deep neural network, right? So if you, these are the anatomy. If we say this is the red shown in the red color is an input layer, here we will be giving the inputs, and these are multiple hidden layers. So if input of the previous layer is going to the every neuron in the next layer, so then the layer we call fully connected layer. So right, these are all the hidden this particular deep neural network has one input layer, 4 hidden layers, and an output layer which is producing 4 outputs. So one of the important concept here is actually deep learning is all supervised learning. So one important concept comes the loss function, right? So in the case of supervised learning, as we have discussed previously, that we have a data set plus their associated output, right? So what neural network is learning, neural network is approximating the function. How do we associate these input to these output, like how these by varying how much these weights across different networks, how these inputs can be mapped to the output. So loss function, like here we can say that these are our input features, like this our input has 2 features maybe, and these are so many training samples, maybe millions of training samples, right? And we have their corresponding outputs, like if the input features are 4 and 5, the output of this should be 1. If the features are 2 and 1, the output should be 0. 5 and 8, output should be 1, right? So once we give these inputs to our trained neural network, or when we start training of our neural network, it produces some output, right? For input 4 and 5, it might give the output as 0.1, right? But the actual output may be 1. So loss function is like over the all input functions, what is the deviation between actual output for the given set of inputs and the output produced by the model. This is what we call the loss function. So there in the network, while training the neural network, we try to minimize this loss, like loss, the difference between the output, actual output, and the output produced by the model. So optimizing this loss so that we reach to a state where the output is minimum is what we all about training the neural network. This is how does a neural network work, right? So initially we have, so this is all about, this is neural network is just supervised learning here. So here our input may be our an image, right? So like this is an image of cat. So here the output may be like, suppose this is, we are doing using one hot vector encoding. So like this is a one hot. So here they say that if an image is shown as cat, so this output it should produce this as one output one, right? So we will give the input to our neural network, right? So initially the weights and biases of or different layers will be the random, right? So the model will produce an output. Say we say that y hat. We know the actual ground truth that whether this is the image of cat or dog, right? So then we will compare the what output produced. So these comparisons need to be made in terms of numerical values, right? So the model produces some output, and with the help of loss function we calculate how much they differ, right? How much this the output produced by the model differs with the ground truth, right? So this is what we called loss, and we calculate the gradients, and with the help of gradient we try to adjust the weights and biases of different layers so that we get the output which is nearer to the actual value, right? So this is how the training of neural networks this is how a neural network gets trained. So we give it an input, so it produces an output corresponding to that given inputs, right? So then we compare the output produced by the network with the ground truth, right? So based on then using an algorithm called backpropagation and gradient descent, we adjust the weights and biases of different layers of our neural network so that the output produced by the network is similar to the ground truth that we do for the all training samples given to us. So over the different this training loop, these weights and biases gets adjusted to minimize this loss function, right? So there is another kind of neural network what we call convolution neural network. So convolution neural networks are specifically designed for computer vision jobs. Like these work as like, how do we identify that this is a face, right? So we just look for certain patterns like eyes and nose and shape of forehead and so on, like, so these are called the features of a face, right? So as our brain looks for these features and tries to classify whether this is a face or not. So similar to our there are convolution neural networks which are used in, so convolution neural networks are basically used for image recognition. So they have these so they try to identify these features automatically from our image. While training, they try to extract these features automatically from the given set of images. So the features may be very low level features like edges. Then from these edges, then it tries to learn the mid level features like ears, nose and all. Then when it combines these mid level features together, it may try to construct or identify high level features like faces, right? So in computer vision, convolutional neural networks are used for image recognition or image classification, whatever you so these are some popular CNN architecture. So these are some popular CNN architectures. So once we give an image, so there will be convolution filters. So initially there will be very less number of features in that. So if you generally see any typical architecture of a convolutional neural network, so an input image is given. So initially there will be very less filters or very less features it will try, because low level feature will be very less, maybe edges only we just trying to identify. So initially the features will be less and spatial dimension will be more. In the next layer what we will do, we will reduce the spatial dimension and increase the number of features or convolution filters. So this way we keep on increasing, like we just increase the number of feature and reduce it dimensionally. Spatial dimension we keep on reducing, and finally we will be connecting it through some fully connected layers, and produce an output like classification or whatever we want to do. So this is what we call pyramid architecture of CNNs. The pyramid architecture, because initially we will have high spatial dimension, then and low number of feature maps. Then we will reduce the spatial dimension but increase the features, right? From the low level features we will just try to create higher level of feature and more number of features. And these are most popular and successful architecture of CNN. So this is one of the AliNet 5 architecture, this which we will be implementing in our practical. Right, so now if we discuss about various tools, or we'll be basically talking about open source tools in the Python which are available for deep learning and frame learning. So like if you learn NumPy, SciPy, Scikit-learn, XGBoost, TensorFlow, Keras, PyTorch, Stats Model, Caffe, OpenCV, AutoML. So these are different deep learning or machine learning models which are available in Python open source. So you can just search on the internet and you get a lot of material on this. So Scikit-learn is one of the most popular and powerful and versatile open source library for machine learning. So it has all things like supervised learning, unsupervised learning, SVM, everything is implemented in Scikit-learn. This is one of the easiest libraries to get started with. Then TensorFlow is an open source framework that has gained popularity due to scalability and use. So it was developed by Google Brain team. So TensorFlow uses tensors to represent data, right? And you can know more. Also, TensorFlow is one of the, like if you are going to develop for production model, you can use TensorFlow. And suppose if you want to go specifically for geospatial, if you want to use deep learning geospatial domain, there are multiple libraries. So one of them is TorchGeo. So you can explore TorchGeo also. It can be used for land cover classification, object detection, change detection, disaster response monitoring, urban planning, like whatever you can use geospatial data. So same thing, you can implement those models for doing that particular task using Open TorchGeo. Then there is another called EOLearn. So EOLearn also act as a bridge between Earth observation and remote sensing field. So EOLearn also, you can actually it can help you bringing the geospatial data in a format that is easily ingestible in deep learning models. So EOLearn also you can explore, because of the paucity of time I am not able to explain to more of this. So one of the popular tool is Raster Vision. Raster Vision also is an open source Python library and framework. Actually it is both of a framework as well as library for building deep learning models. It can be used for deep learning on satellite image, forecasting rip currents, like whatever you can use with deep learning, you can use Raster Vision also for all these tasks. So like it automatically it supports object detection or classification, segmentation, right? So geospatial data, like what is geospatial data? So you can say that geospatial data is the information that describes objects, events or features with location on or near the surface of Earth. So that's what we call geospatial data. So geospatial data can be represented in two formats. One we call raster, another one we call vector format. So today's demonstration I will be just concentrating on the raster format, or what we call image. So for this demonstration we will be using one of the most popular deep learning framework, that is PyTorch. So PyTorch is an excellent open source platform. It has been developed by Meta's AI research team. It is an open source deep learning framework. It supports CPU and GPU computations. It enables users to create dynamic computational graphs. I think the dynamic computational graphs used in TensorFlow are static, but PyTorch supports dynamic computation graphs. It supports distributed training across multiple GPUs. If you have large data sets on which you want to train your model, and if you need multiple GPUs, then PyTorch supports multiple GPU training. Then PyTorch is well supported on all major cloud computing platforms. If you are going to use Google Colab, PyTorch comes pre-installed in the Google Colab. So I'll be using Google Colab for today's demonstration. So these are the key capabilities. It is production ready and it supports distributed training. It has robust ecosystem. There are a lot more other libraries, a full ecosystem of tools and libraries extending the capabilities of PyTorch are available, like PyTorch there are many more, like as I said that if for deep learning we have raster vision and torch geo. Then it's a cloud support, like all major cloud service platform, they are supporting PyTorch. So this is one of the basic these are some terms we'll be using quite frequently. One, what we call classification. So the classification, the classification term used in parallels of deep learning is slightly different from the in the what the people in remote sensing domain say for classification. So in case of in case of deep learning, classifications mean, like suppose this is an image, and if this particular image contains a dog or dog image or cat's image, so that what we say in parallels of deep learning classification. So the say like, so classification is like whether this particular image contains a dog or not, matter of where it is. So that what we call classification. So then when we are locating that particular object in an image, maybe cat or dog, so that we call object detection. So classification is just like whether this is an image of cat or dog, is there a cat or dog in that image or not. When we localize that object what we are looking for, right, so that what we call object detection. So like drawing a bounding box around that. So then the term comes segmentation. So when we actually, for every pixel, if we tell that if this particular pixel belongs to that object or not, so that what we call segmentation. Like here you can say only the pixels which are belonging to that image, that dog, are in red, right? So this is what we call segmentation. But this is what we call classification in image remote sensing parallels. So today we will be using this classification, not the classification in terms of what we call what remote sensing community says. So we will be doing a classification what deep learning community says. Right? So we will try to identify different land use or land cover patterns in our satellite image. So we will be using one, I will be explaining as we go. So for this, as I said that you must have some basic understanding of Python. So PyTorch is, as I said, is one of the most popular framework for using deep learning. So if you go to Google Colab and log in with your credentials, by default PyTorch or Torch comes installed to that, and plus it gives you access to GPU as well. So if I say I'll connect and start, I have taken much more time than what I thought I will taking on the lecture. So now anyway I'll go a bit fast on the code pattern. So I'll be just explaining. So first thing, once you installed PyTorch, so you need to import that. So Torch is the name of the package, and NumPy. So equivalent to NumPy, there are tensors in deep learning terminology. So tensors are similar to NumPy's ND arrays, except that these tensors run on GPU or hardware accelerators. So NumPy arrays are not designed for running on the GPUs where parallel processing takes place. So like you can say that tensors are equivalent of NumPy arrays which can run on GPUs, right? So these tensors are multidimensional arrays. So how do we create? So all images, all objects or images, whatever use, are represented as tensors in deep learning. So anything, any data what you are going to use for deep learning are represented as tensors. So as I said, the tensors are as NumPy arrays. So like this is a NumPy array, I am creating a two-dimensional NumPy array. Suppose if I want to convert this NumPy array to tensor, then I can just call torch.tensor and pass it the data format which I want to create a tensor. And so if I just run x_data, so it says that this is a tensor of, like, this is quite people who know NumPy already. So NumPy arrays and tensors are, they offer all similar functionality, but difference is tensors run on GPUs. So similarly, suppose if you want to create a tensor from a NumPy array, you can just call torch.fromNumPy and pass it your NumPy array. It creates an tensor from a NumPy array. So NumPy arrays are tensors are the basic building blocks of a neural network. Not neural network, actually are we use actually entire day for representing the data. These are the building blocks for representing the data. So building block of the neural network is a neuron. So for this I will be using another library, as I said, that torch geo. Actually the dataset available is not by default is not available in PyTorch. So the dataset which I will be using is available in torch geo. So because of that I am just installing the torch geo. So as I said that let it get installed. So basic building block of data is tensor. So all data which you want to use in a neural network must be in the form of tensors. And so there are the different utilities available in the PyTorch for handling this data. So PyTorch has two primitives to work with data. Two primitives. One is called data loader and another is called dataset. So dataset stores basic samples and corresponding labels. So like every image and its corresponding label will be stored in, and all these samples will be stored in something called dataset. So but while training the neural network, we need to make the group or batches from this dataset. Like if there is something called mini batch gradient descent. So like for training the neural network, we need to group these individual images or their labels into groups together. So data loader helps us in creating groups or batches of the batches from these data sets. So these are two basic primitives. One will is called data set. So data set will be your actual image and its label, and the data loader will help us in grouping these data sets together. So now this torch geo got installed. So I need to just restart. So for using this, you need to just import torch. So torch is our base package, and from torch we are importing another package called NN. So NN is the package for implementing neural networks. Then data loader is available inside torch.utils.data, and torch vision dataset actually we don't need anyway, just import. And if you want to convert some datasets, so for this particular demonstration I will be using a dataset called Euroset. So I will be talking about this in detail. So like if you click here, it shows the detail about this, right? So now first thing, you need to import all these packages. So now as I said that these all Euroset is a dataset. So I will talk in this now. Suppose now if you want to download this dataset, so this dataset is available in torch geo. So I'll just create an object of this training data equal to Euroset 100. So this dataset contains only 100 images. So and that is split in to training, validation and test datasets. Right. So I am telling root equal to data to store this data into the data directory, and I want to just download the training images. Like Euroset contains some multiple images. Some of that images are marked for training, some are marked for validation, and some are marked for testing. So I am just downloading the images which are marked as training images. So if I just do this training data, so it is downloading those data from the, and now similar way I am validation dataset I am just downloading for validation. So this is the description of Euroset dataset. So what does this Euroset dataset contains? So Euroset dataset is based on Sentinel-2 images covering 13 spectral bands. So these all images, whatever are available in this particular dataset, these are the images of Sentinel-2 spacecraft, and these has all 13 spectral bands which we get with, and with this every image we have 10 target classes, or what we call the classification of that image, whether this particular image, what this image represents, whether it represents a highway or a green pasture or a forested area or something like. So this is not the classification. This is not the classification what people in remote sensing community say. This is classification in terms of deep learning community. Right. So the Euroset dataset contains Sentinel-2 images of 64 by 64 by 64 of the size 64 by 64, and they have all 13 spectral bands, and label is the land use pattern of that particular image, like whether this is a highway or this is an industrial building or residential area or something like, not the classification in terms of what remote sensing community says, right? So this has this we have 100 64 by 64 64 cross 64 images with 13 bands. We will see and visualize these images. So these are the land cover classes. We say annual crop, forest, vegetation, highway, industrial building, pasture, permanent crop, or whatever, right? So this is was just I have just because in image, as I said, that either image or label will be represented as tensor. So tensors are numeric values, right? So these labels of every image is stored at a number from 0 to 9. So just for showing, like, 0 number is means if there is, if with image the label attached is 0, so that is what we call annual crop. One may be forest. This is the label attached to that map. So we have just created a dictionary which maps from the numeric tensor to its textual representation. What does it, right? So I'll be using a matplotlib for doing this. Now actually now we can see that we have downloaded the data set, right? So training data is our data set which contains all images. Like if I see the training data set dot shape, or so I'll say training actually this is not, it will not give me the shape. Training data 0. So now you can say that this all training data are represented as an image of 64 by 64 cross 33. So 13 bands are available, right? So now suppose let's visualize these images, like some random images we will take. Our data set contains, like if I say len of data set, sorry, training data. So 60. So sir, there are 60 images of this, like 16 to 34, 30%. Now suppose let's visualize few of these images. So this is the part of matplotlib anyway, is not important for this. So what here I am doing, just I am creating 3 by 3, 3 rows and 3 columns, and I am iterating over this, and just I am generating some random number out of these 60. I am just picking up some random numbers and plotting them, right? So if we see these images and attaching that label to that, if we see, so this how does our training data looks like, right? So this is an image and label attached to that image is forest. Actually I have taken a single band, some of the band from that, like this is an image and this is classified as highway, right? So this is also classified as highway. This is permanent crop, forest, sea and lake. So this is our training data, contains image of 64 by 64 size and 13 bands and a label associated to that image, like what is it is, that is also in the form of numerals 0, 1, 2, 3 or whatever, like. So suppose if similar these images, because there are 13 bands, out of 3 bands, suppose if you want to create a false color composite or standard false composite, so this is how these images look like in a false color composite, right? So this is a bit clear, like this is industrial building, you can say quite clearly, and this is highway, and these are also classified as industrial building, and this is a river, right? So this our training data looks like this image and its associated label. So image is stored in tensors, even label also is stored in a tensors form. Right, now the second thing I said that this, because this data set contains all 100 images. Right, now for training a neural network we need to group them in batches. Right, so for that there is a function, a utility called data loader. Right, so for every data set I am creating a data loader which I am passing the argument like training data or like my data set, which needs to be grouped together, and batch size. So what should be my mini batch size, like 4 images to be together, and if I want to do shuffling on that, then I can do shuffling. So I have now created 2 data loaders. One is for train data loader and another is test data loader. Right, and now if I iterate over this, now it says that now you can say that our batch contains 4 images, right? 4 images and 4 labels. Now if I inspect the sizes of these, it says the size of image is 4 cross 13 cross 64 cross 64. 4 images, 13 bands or 13 channels in every image, and the image size of 64 by 64, and there are 4 label attached to every image, right? For in case of supervised learning, we need image as well as its attached label. Now let us see how do we build a model. To define a neural network in PyTorch, we create a class that inherits from the NN. So NN will be our base class NN. So whenever we are creating a new model, we need to inherit this NN model. So we define the layers of network inside the init function and specify how data will pass through the networks in the forward function. So we will be for implementing a neural network, we first need to inherit NN class, and inside that we need to write a function called forward. In that we will specify how the data should be flow in our side. So suppose if you want to use GPU, right? So it is quite simple because right now I am using T4 GPU available with. So there is like, if you can use you can store it, like you can just say torch.CUDA available. You can just query if CUDA is available in your system, then you can use GPU for processing. Otherwise, you can just use CPU. So here I am creating a variable called device. In that, if CUDA is available, I will be in the device. I will be using device. I am storing value CUDA. Otherwise, CPU. So because now I have used GPU is available to me, say that using CUDA device. So the whatever model we will be training or running, it will be running on the GPU. And this is how do we define a neural network in PyTorch. So first thing, I am creating my model. So for model, as first thing what I said that we need to first import NN. So NN.module, we need to import extend actually or inherit from the NN.module model. So this is inheriting NN.module, and inside that we are defining the constructor init constructor, and inside that this is the calling it superclass constructor. So first layer what I am adding here, flatten lap, right? So as I said that our image now is a 3-dimensional image, right? So first thing, as I said that neural network we need to convert into a single dimension. So this NN.flatten layer converts our 2 or 3-dimensional image to a 1-dimensional set of inputs, right? So then now here we are creating a set of layers. So first layer we are calling here fully linear layers. Linear NN.linear is a fully connected layer. So to this NN.linear we need to specify 2 parameters. One is number of inputs and another case is number of outputs, right? So in our case, our image, we just wanted to pass every image to our neural network, right? So our image is of size 64 by 64 and there are 13 channels. So if we flatten it, so how many pixels will be there in our every image, or what every pixel or values in all bands, if we say call a feature, right? So every pixel has, now we can say 13 features we can say. Now there are, but there are 64 by 64 pixel in every image. So right, so the input layer will have, so these many input parameters like 64 multiplied by 13. So these many input features will be there to our layer, and these in our first hidden layer we want to have 512 neurons, right? So right, so this is the size of input and this is the output. So this is the size of input and this will be producing 512 outputs. Then we are applying a ReLU activation function to the every neuron, right? So then again we are creating another hidden layer that has now these 512 inputs, because we are creating fully connected layer. These 512 input layers will go as input to the next layer 512, and from this we are producing 128. So now there will be a third hidden layer with 128 input layers, then neurons. Then we have connected activation function, ReLU activation function to this. Then again these 128 inputs are going to another layer which has 32 inputs. Then again activation function, and finally we are connecting these to 10 outputs, right? Because we wanted to predict to classify these images to one of these 10 classes. So if you are just doing binary classification, you can do 1 or 2. So depending on how many classes you want to classify your data into, so you can choose that how many output layers should be there. Like right here we are producing finally 10 outputs. So this is the architecture of our neural network. So it has, you can say, 1, 2, 3 and 4 hidden layers, and finally finally one output layer. So in the neural network we need to specify one something called forward function in. So def forward, so first anyway is self, and this input will go to this. So whatever input, while training, this input goes to the forward function gets called automatically. So first thing, what, like now here we will specify how the data should be passed to these layers. So first whatever input comes to the neural net to our model, so first it should be go to the flattened layer. So whatever input is coming, first it will be flattened out by this flattened layer, right? So then self dot linear ReLU stack. Now next, this x, whatever after flattening in, this x goes to this ReLU stack where there are multiple layers. So finally this will be producing an output. So whatever it is producing, we will be storing in the variable logits, and this forward function returns logits, sorry. So then this way we build our model, right? So once this is the framework of our model. Now we need to create an object of this model. This is, we have just defined a class, right? So now by calling neural network, we create an instance of this class or an object of this class, and if you call this dot to, so if you have already available to GPU, we are transferring it to the GPU. If there is CPU, then it will run on the CPU. So now if I see model, I have not run this step. So here I have created a model. Now if I just inspect this, I say model. So this, you can see that this is the input, like this is the structure of our model. So first is a linear layer which has 523,248 input features, right? So these are all our 64 by 64 pixels in our image. So those all are being used as the features. Then this has 512 outputs. Then the next layer, these 512 which go as input to the next layer, and it is producing 128 outputs. 128 going 32, finally 10 outputs are there in our level. So next we need to specify a loss function, right? So how our neural network check the quality of the output produced by the model, right? So there are different loss functions for that. So generally for classification, we generally use a function called cross entropy loss, right? So first you need to specify the function nn dot, like here we are using cross entropy loss. Suppose if you are doing a regression, you can use MAE or MSE also as a loss function for training your neural network. Then there is something called optimizer. So optimizer is what will be updating the values of weights and biases based on the optimizer will be manipulating the values of weights and biases of the different neurons based on, for optimizing the loss value, right? So this is like how to create an optimizer. Torch.optim. Here we are creating an gradient or SGD, stochastic gradient descent optimizer. So here we need to pass in the parameters like models parameters of the model by calling model.parameters, and another argument called learning rate, how fast or slow the model must learn or change the weights, right? So once we have created the model, then we specified our loss function and optimizer for this model. Now we need to train the model. So for that we have written here a train function, right? So to the train function we are just passing the data loader, right? So the data loader which has batched our inputs into the batches, and the model on which it should be trained, a loss function and an optimizer, right? So first here I am just calculating size. So first thing, for training the model, you need to call the function called model.train. So once by this switch, model is into the, so here it will be tracking the gradients. So model.train. So now our whole training data set is broken into the batches. Now we will be iterating all over those batches one by one, right? So with the enumerator we are just batching over all the image sets. So like image data and image So this is our actual, like in the image data, actually this is we have specifically used the data set of torch geo. So it stores it as a dictionary which has two keys, one is image and another is label. So image key contains the images and label key contains the labels. So I am just fetching the images and storing them in the x variable, and fetching the labels and storing them in the y variable. Now because these are existing in the CPU, we need to transfer them to the GPU, because our model has been transferred to the GPU. So like by calling x dot to and passing on the name of device where you want to, we are transferring it to the GPU. Right, now we have just fetched our data and its associated label. Right, now initially at the first time all our weights and biases of all our neurons will be have some random values. Right, so with the random value, first what we are doing, first we are passing on whatever input images we have, and it will produce some output with those weights and biases, those random weights and biases. Right, so then it will produce some prediction, it is generating some prediction. Now here we are comparing this, the output produced by the model with the actual output. Right, so that with the help of loss function we are quantifying how how our prediction differs from the actual values of that land class. Right, so with the with the help of to the loss function we are passing the predicted value and the actual value, and we are quantifying the difference between their values. Right, so then once this is done, once we have quantified, now we need to calculate the gradient, so that like how to how much the weight and biases should be updated. So for that, if you call loss dot backward, so in this case the neural network back propagation will be done, and new biases like new biases and weights will be calculated on that. Right, so if you call optimizer dot step, so then it will update the weights and biases by the optimizer. Then actually after that we need to zero the gradients. Right, so this is the model, like then this loop keeps on going. Right, so like this after this we have calculated the loss. So based on this loss, the optimizer will decide how much for each neuron, what how its weight and bias must be updated by the optimizer dot. In the optimizer dot step function, those weights and biases will be changed. Right, so then it goes to the, then we go to the next training set. Again the same process will be followed. Right, so this way this loop will keep on going until we iterate over all the data in our data set. So right, the next time, now we expect that the loss to be because weights and biases, because we are updating the weights and biases for minimizing the loss. So this way we will keep on repeating this to the number of times we have specified the number of epochs. Right, this is the training loop, how the neural network gets trained. So once a neural network gets trained, we need to test it for the data which it has never seen. Right, because anyway training loss will be keep on coming down. So now finally this is the testing loop is similar to our training loop. Only thing, the difference is there, before calling that there it was model dot train, now we need to call model dot eval. So in that case it doesn't keep track of gradients, and the same thing is here we need to call with torch dot no grad. So in that case it doesn't keep track of gradients, because now here we are in the testing loop, we are not updating the weights and biases, we are just giving the input data and getting the inference from the model, and we are comparing that just with the actual outputs. We are not updating here weights and biases, so here we are not tracking the gradient. So with torch dot no grade, and the steps are almost same only here we are just comparing the predictions made by the model to the actual prediction. So that gives the about the accuracy of our model. Right, so anyway this is the same step. Now suppose if I want to train this particular model for 10 number of epochs. Right, one epoch means when the entire data set is scanned for at least once. So one, like if our model in the training mode phase, if our model like has scanned over all the data sets all the samples in our data set, that what we call one epoch is completed, like all batches have gone through the cycle, then we call an epoch. So like for this, then we keep on training for the different number of epochs. So here I am training the model for 10 number of epochs. You can change, right? So first, in the first epoch, first we are training the model for, like in one epoch, train for the entire data set, then test, or what you can say here, validate actually basically. So train, then test, then again in the second epoch and third epoch, like this we can go, and we expect that the loss will be coming down over every epoch. Now suppose if I run this, oh, actually I have not run these steps. So now you can say that the accuracy of our model slightly increasing, 10 to 15% it has gone, right, but it is stable to, like here you can see that the loss is coming down with the every training step, right? So initially the loss was, when first batch was given for training, the loss was 126, but in the second it increased, but once the training gets stabilized, you can say somewhere here the training got stabilized, and now the loss is getting reduced, and the accuracy on the test data also is slightly increased. Accuracy, it has not become stable, like if we because the whatever model we have made is just a toy model, it may not be suitable for the data set which we have, right? But we can say slightly that the accuracy is increasing and the loss also is increased, like loss accuracy also is fluctuating between 10, 15 to 20, because our training our network also is not so powerful as of now. So like this is just for a tutorial. This way we can build and train our neural network. So our objective is here is to minimize, so the accuracy, what, so the loss must be similar on both training set as well as testing set. Now here we can see that for this particular data set, the, like where if we see the loss is more on the training, but it should is greater than, but here almost both are similar. So with this we can say that the model is not overfit, because the losses on training set and the test sets are also similar, so similar in the similar range. So we can say that the model is not overfit, like. So now after 10 epochs we can say that the model is up to say 15%, on average it's 15% accurate, right? So if we make the, or give it more training samples, or if we train it for more number of epochs, we expect the accuracy to increase. Now let us see how do we use this particular, now the model is trained. So model is trained means it has selected the best weights and biases for all neurons to get the, to approximate the function, or for the minimum loss, or like to approximate the input features to the output, right? So now we can say the model is trained means all biases and weights have been calculated to their best value to, for getting the minimum loss or maximum accuracy of the model is, well, now the model is trained. Now all weights and biases are calculated, and now when you can save this, or this model you can use for prediction, right? So the prediction you can use the similar way, like model, and if you pass it a new value, it makes a prediction for that. Now suppose if we take a random sample from our training set and see, because the model is 15% or 10% accurate only, we may say that out of 10 images it may just predict only one image correctly, right? So now here what I have done, I have just taken random image, I have sampled as a random image from the test data set, and predicting, and features of that we are giving to the model, and seeing that what the model is predicting, right? So actually we have given the industrial building as input to the model, but it has produced the river, because the accuracy was quite poor. But if you say for the next time, so if I run next time, it has shown river as river, right? Now let us see with image. Right, so instead of that I have actual image. So now you can say actual was permanent crop, but it has predicted as a river. Now if I run for the second time for some other random image, so pasture it is showing as river. Now vegetation it has, so none of the image I could get correctly classified. At least one I hope to get correctly. No. No. So anyway, here at least I got one river per river, but when I'm giving some more images, it is not able to predict. So, but because the accuracy of the model is quite poor, so this way we can see that how can we build a model and test the model using PyTorch. So similar way, because generally for image classification tasks we use neural networks. So then actually because now time is not available, so then similar way we can use implement CNNs, whatever architecture we have seen here. So for that we have this convolution layer. So with the help of convolution layer we can build a convolution neural network, which basically we can use for neural network. So similar actually this is some old run of this. So suppose if I want to build a neural network of this size, so like I can create like this. So while specifying a neural network, you need to specify these three parameters, right? So first is your number of input channels. So you can say here, or first convolution layer is getting 13 input channels. The image, let be the image size of image be anything, then it is producing 6 feature maps, right? So it gets 13 channels as image input, and it produces 6 feature maps, like it is trying to learn 6 match. So first neural convolution layer is trying to learn 6 features, and it is using a kernel of size 5 by 5, right? So first convolution layer, then there is a max pooling layer. I think it was discussed in the convolution layer CNN lecture. So now, as I said, that all popular CNN architectures are like, first we give the entire image and less number of feature maps it generates, then we reduce the dimension. So right, so here now we are max pooling, or we are reducing the spatial dimension by 2. Then in the second layer, now it has generated 6 feature maps. Those 6 feature maps are going as input to the next layer, and it is producing 16 feature maps, right? So now we have reduced the spatial dimension and increased the feature maps. Then kernel size is same, and now next these then we may further reduce the spatial dimensions, and now we have again another convolution which will be getting these 16 feature maps, and it will be producing 120 feature maps, right, from 60 to 120, and it is also using the same kernel of 5 by 5 size. Now finally we have these fully connected layers. Now let us see how this particular network works. This also may perform similar way only. Now the training functions are same, and our loss function, everything is same. So this is our architecture of our and suppose if I wish to train it for may say just 10 epochs. So the accuracy of this also is in similar range, 10 to 15%. So what is required here now? We need to improve our architecture of our model to get better results. So let us see if it produces something. No, this is also producing quite wrong results. So here CNN also could not work. So at least one image, I think sea or lake, I could get it correctly, right? So this accuracy was 10 or 15% only. So this way we can implement basic neural deep neural networks or convolution neural networks using PyTorch. So this was my all in this lecture. So with this we come to the end of this lecture. If you have any questions, you can pose it on the chat box, and we'll try to break. So thank you very much for attending. हाँ लिखना यार क्वेश्चन वो है वो ई क्लास चल रहा हो तो लोग तो कहते नहीं चल रहा नहीं चल रहा क्या है E8 अच्छा अच्छा So welcome back. So I will try to answer few of the question with best of my knowledge. So some of the answers may be incorrect as well, right? So I will try to answer. So I beg your pardon for that. So so I will try to answer with the best of my knowledge. So few questions I will take. The first question. What is asking is, can you please repeat the concept of optimizer? As I said that the uh, objective of training in a neural network is we have to minimize the loss, right? So how the output produced by the model is, so there must be a close match between the output produced by the model and the actual output, right? So for that we need to update the weights and biases of different neurons in our network, right? So optimizer does that job, right? It does the job of optimizing the loss by changing the weights and biases of these different neurons. So that is done by something called, by calculating, it calculates the gradients. So there is an algorithm called back propagation. Actually, you can read more about it. So these optimizers use back propagation for calculating new weights and biases of every layer or every neuron in the network to make the loss minimum, right? So optimize, the job of the optimizer is to update the weights and biases of every neuron to get the minimum loss. How would you evaluate the performance of classification model in the Python? So actually there are different matrices for evaluating the performance of a model in Python. Suppose if you have a binary classification model, right? Suppose if your model is binary class, doing this binary classification, then you can do these matrices like true positive rate, true false rate, F1 score, true positive rate, right? Accuracy, F1 score. So these are some matrices which we can use for, if you are using a binary classification model. For regression, they are like MAE, MSE, these matrices you can calculate, or kappa coefficient. So there are different matrices for evaluating the performance of a model, like that will be the part of testing your model. So you can choose different matrices depending on what kind of model you want to evaluate. So how do we train a neural network to improve its accuracy? Right, so actually there are different approaches to that. First, you need to improve the quality of your training data. Then you need to experiment with the different hyperparameters, like maybe batch size, learning rate, and number of neurons in different layers, different optimizers. So actually this is a more of, when you experiment with different data sets, then only slowly you can improve your accuracy. There is no answers which I can tell you that this is the way to improve the accuracy of your network, right? So you may need to change the architecture of your network. You may need to tune the hyperparameters such that you get the better accuracy. You may need to use some regularization. There are different techniques. So actually you need to experiment with different things to get the better accuracy. There is no direct answer to this question, as far as I know. So then there is a question like, how do you split the training and testing data sets in Python? So suppose depending on which library you are using, either you can do it manually yourself, or if you are using some specific library like scikit-learn, if you are using for machine learning, scikit-learn has a function for test and train split. Similar way, PyTorch has a function. This function you can see on the screen, random split. So random split, with the random split you can split your data into the training and test set using this also. So the basic convention, actually there is no universally accepted for this also. Like some people say 70% you can use for training, 20 for validation, and 10 for testing. Some say 60, 30, and 10. So there is no universally accepted answer to this. So generally the basic approach is like 70 for training, 20 for validation, and 10% they take for testing. So how do we define the proper batch size as per our data set? As I can say that there is no right answer to that as well. So batch size depending on how much memory GPU in the memory available to your GPU is there. So batch size is a hyperparameter. So there is no definite. So you just need to just experiment with different batch sizes, right? So that mini batch size is a hyperparameter. You need to experiment with different batch sizes, maybe starting with the minimum. I think is there. I am not sure if there is any thumb rule for deciding the batch size depending on the data set. I am sorry, but in general, you need to experiment with different batch sizes. How do you decide the number of channels? So the number of channels are decided by the inputs you have, right? So in the example I have shown, I have 13 band input image. So definitely there the number of channels are going to be 13. So if I have if I have just a RGB image, then in that case the number of channels will be just one number of channel. And if I have a grayscale image, then the channel will be one. In the case of RGB, it will have 3 channels. In case of a grayscale image, it has just each epoch 4 losses. So there, like in epoch, we were calculating the loss for every batch, right? So when we say an epoch is completed, when all the training samples are at least gone once for the training, so that we can say that one epoch is completed. Now we assume that our maybe our batch size was 4 only, and suppose if our images were 20, so we will be seeing that 5 times the loss is getting printed. Like for every batch we were calculating the loss and printing the loss, so because of that we were saying the loss will be 4 or 5 times for every batch. So with increasing the epoch accuracy, or there is more on the, so actually by increasing the number of epochs, definitely the accuracy increases, but the accuracy may increase just on the accuracy, or loss accuracy may increase just on the training data. But if you actually basically accuracy depends on both the things, right? Number of epochs as well as the architecture. So like if your architecture is poor and if you train it for many number of epochs, so what may happen, your model may just learn the data, like it might overfit. So your model may perform quite well on the training data, but it may not perform good on the validation or test data, right? So that's what we call overfitting. So accuracy of the model is, you can say, is just a combination of both, like your good architecture plus the number of epochs you train it for. Like there must be a balance between both of these things, like how much layer we should use in any deep learning model creation. So once I read somewhere that creating a neural network is more of an art than science. So there is like no, as I said, there is no general rule of thumb or general answer for like how do you decide how many number of layers you should use for your network. You need to experiment with different architecture, different number of layers, and choose what works best for you. There is no generalized answer like one number of layers might good for me, for my data set, but it may not be good for you. Like then there is no generally thumb of rule type of thing. You need to just experiment with different number of models on with your data set. So CNN helps to match the fingerprint of a person. See, for finger matching, I think you may not need, with simple image processing also finger matching can be done. CNN may not be required for that. CNN sometimes maybe, I think maybe overkill for that. So these were, I think these were all the questions. So I thank you very much for attending the session. So with that we come to the end of this entire course. So I think, I hope it must be useful to you all. So with that we sign off from the session. So thank you very much for attending.